In this video, we're going to do a few examples of hypothesis testing for a proportion. So for each of these examples, I'd like you to answer the following 4 questions. First of all, is this a one-tailed test or a two-tailed test? And for that, we're saying, all right, when we're testing a claim about a proportion, are we just interested in whether it's like just less than the specific value p that we expect, or are we checking if the sample proportion is just different? Has it changed? So this one-tailed versus two-tailed is going to be based on the language of the claim that we're testing. If we're testing something like changed, then that's two-tailed, versus if we're testing something like is less than or is more than, then that would be a one-tailed test. So it's going to be based on the language of the experiment. Then we want to write the null and alternative hypothesis for the experiment or study. Remember that the null hypothesis is nothing has changed, or the expected proportion is still true, versus the alternative hypothesis is generally the hypothesis we're testing. Is the new proportion greater than it had previously been? Something like that. Then we want to find the p-value for the statistic. That's the probability of a result at least that extreme. To find the p-value, we are going to look at the sample proportion. That's p hat, and that is the number of successes or the number of yeses or whatever divided by the number of trials, x divided by n. We're then going to find the probability of observing a sample proportion at least as extreme as that, given that p is the true population proportion. So if we're looking at observing a sample proportion that is less than p, then we're looking for the probability of a result at least as extreme on that side. And if we're looking at observing a sample proportion that's greater than the expected population proportion p, then we're looking for the probability of observing a result at least that extreme on that side. And if we're doing a two-tailed test, we're going to multiply that probability by 2, because then we're interested in the probability of a result at least that extreme on either side. So to find that probability, we'll find the z-score. The z-score is in general, the data value minus the mean divided by the standard deviation. So if you're using technology, you could just use p hat is your observed value x, and p is the mean for the distribution, and the standard deviation will be this. The standard deviation assuming that p is the true population proportion, so that standard deviation is going to be the square root of p times 1 minus p divided by n, the sample size. So if you're using technology, you can use those 3 values, or if you're using a z-score chart, you can then find the value for z, the sample proportion minus the population proportion divided by the standard deviation, and then use that z-score table to find the probability of a result at least that extreme. Finally, what should the researchers conclude? Should they reject the null hypothesis or not? And what does this result mean in context? So here are a few examples to try. So here's an example to start with. 10% of the general population is left-handed. A researcher wants to test the claim that artists are more often left-handed. They survey 500 artists and find that 68 of them are left-handed. Use an alpha equals 0.01 level of significance to test the claim that artists are more often left-handed than people from the general population. So pause, try that out, try to answer those 4 questions above, and we'll talk about it together. Okay, is this a one-tailed test or a two-tailed test? So we're testing the claim that artists are more often left-handed. So we're just interested in, what's the probability of being up here, that they're more often left-handed than the general population. So we're getting some sample proportion, and then we're testing what's the probability of a result at least that extreme on this side. And so here the key word is more. not just differently handed, but more often left-handed. And so therefore this is a one-tailed test. Now we want to write the null and alternative hypothesis for this experiment or study. So the alternative hypothesis is always what we're testing. Here we're testing the probability that P is greater than 0.1 for artists. So we're testing the claim that artists are more often left-handed, that the true proportion is greater than 10%, is greater than 0.1 for artists. And the null hypothesis is that basically the proportion for artists is still 10%, that 10% of artists are also left-handed. So you could write it as, in words, 10% of artists are left-handed, or in symbols, the proportion for artists is still 0.1. Or you could also write it as P is less than or equal to 0.1. Some resources prefer that this null hypothesis is the complement of the event of the alternative hypothesis, that it includes everything other than P greater than 0.1. All right, so now we want to find the p-value for this statistic. That's the probability of a result at least that extreme. So basically, we need to find, what is this result? Our result was the sample proportion p hat is 68 out of 500. We surveyed 500 artists, 68 of them said that they were left-handed, and if we calculate that out as a proportion, that's 0.136 as a decimal. So we found this result up here, 0.136, and comparing that with our null hypothesis that the proportion is still 0.1, we're saying what's the probability of a result at least this extreme? What is that probability? So to find that probability, we are going to find the standard deviation for this distribution of sample proportions, and that's the square root of the proportion of successes times the proportion of failures divided by the sample size. Again, assuming the null hypothesis is true, assuming that P equals 0.1 for this population of artists overall. So again, this result of 0.136 could theoretically happen by chance. We're looking for the probability that that result happens by chance, assuming that 10% of artists are left-handed. So the standard deviation here is square root of 0.1 times 1 minus 0.1, 0.9, divided by the sample size from our sample, 500. And when we calculate that, we'll get 0.0134. Now, again, you could either do using technology, you could find a normal probability calculator, and here the mean for the distribution is the proportion that's expected by the null hypothesis, 0.1. The observed value is our sample proportion is our data value x, so p hat is 0.136, and our standard deviation would be what we just calculated, 0.0134. So you could do this using technology at this point with those values, or you can use z-score, the z-score standard normal table, and z would then be the data value minus the mean for the distribution divided by the standard deviation. Here that is 0.136 minus 0.1 divided by 0.0134, and when you calculate that out, you'll get a z-score of 2.69. So now the probability of a result at least this extreme is the probability that z is greater than 2.69. So remember, the table always gives things in terms of less than. So 1 minus probability that z is less than 2.69. And now we're going to do, using the z-score table, the standard normal table, this is 1 minus 0.9964. And so that gives us a probability of 0.0036. So we found out that this probability is 0.0036. If you've done this using technology, you should get a very similar answer. And so we found out that our p-value, the probability of a result at least this extreme, is 0.0036. So that is our p-value. Lastly, what should the researchers conclude? Should they reject the null hypothesis, and what does this mean in context? So when we determine whether or not to reject the null hypothesis, we always compare the p-value to the level of significance. So the p-value in this case, significance. So in this case, the p-value was 0.0036, and our level of significance was 0.01. So here, the p-value is less than the level of significance, alpha. Alpha is the level of significance. 0.01 in this case was the level of significance we were asked to use. And because the p-value is less than that, remember that alpha is the cutoff point. So for rejecting or not rejecting the null hypothesis. So here is alpha equals 0.01. So here's a probability of 0.01, and this was less likely than that. So because it was less likely than our level of significance, the probability of a result at least this extreme is less than 1%, is less than our level of significance, and therefore we reject the null hypothesis. What does it mean to reject the null hypothesis in this case? That means that we are using this as evidence to say that this supports the claim that artists are more often left-handed with a p-value of 0.0036. So again, that's saying that the probability of a result, at least this extreme, if artists really are only left-handed at a rate of 10%, the probability of observing 68 out of 500 artists being left-handed is very low, is 0.0036, is less than 1%. And so we're rejecting the null hypothesis. This supports the claim that artists are more left-handed with a p-value of 0.0036. Here's another example for you to try. In 2004, 88% of adults said that texting while driving should be illegal. In a 2019 survey of 224 adults, 188 of them said that texting while driving should be illegal. Use an alpha equals 0.05 level of significance to test the claim that the proportion of adults who think texting while driving should be illegal changed between 2004 and 2019. So pause, think about those 4 questions for this example, and we'll talk about it together. Okay, so is this a one-tailed test or a two-tailed test? We are talking about the proportion of adults who think texting while driving should be illegal has changed. So this isn't, has it increased, has it decreased, but has it changed in either direction? So we're looking for the probability of a result, at least that extreme, different from 0.88 in either direction, and therefore this is a two-tailed test. What are the null and alternative hypotheses? So the alternative hypothesis is always the hypothesis we're testing. So here it is that the proportion of adults who think texting while driving should be illegal is no longer 88%, is no longer 0.88. So in other words, the alternative hypothesis is that the proportion of adults who think texting while driving should be illegal has changed, whereas the null hypothesis would be that P is still 0.88, that the proportion of adults who think texting while driving should be illegal is still the same. So those are our null and alternative hypothesis. H naught is often written as the null hypothesis, and H1 or HA is often how the alternative hypothesis is denoted. Okay, what is the p-value for this statistic, the probability of a result at least this extreme? So what is our result? Our result is that our sample proportion p hat is there were 224 adults, 188 of them said texting while driving should be illegal. So 188 divided by 224 is our sample proportion. And so that's 0.839 when we calculate it out. And so now we're looking for, all right, assuming that the true proportion is still 0.88, what is the probability of observing a result of at least this extreme of 0.839 or less in a survey of 224 adults? And we're comparing that to alpha, the level of significance. Okay, so what is that probability? So to find that, we need to find the standard deviation for these sample proportions. That is the square root of p times 1 minus p over the sample size. We're assuming the null hypothesis is true. We're assuming that the true proportion is still 0.88, and we're finding the probability of this result based on that. So p is 0.88, 1 minus p is 0.12, divided by the sample size is 224, and when we calculate that out, we will get 0.0217. So that's our standard deviation. And again, if you're using technology at this point, you could essentially almost stop calculating there by saying that your mean for this distribution is the expected proportion, 0.88. Your data value is the sample proportion, that's 0.839. And your standard deviation is 0.0217. So you could use technology there with those values, or you could calculate a z-score. Z is the sample proportion minus the expected proportion divided by the standard deviation. So here that's 0.839 minus 0.88 divided by 0.0217. So when you calculate that z-score out, you'll get a z-score of negative 1.89. And now we can use the table to find the probability that z is less than negative 1.89. So that's using the z-score table. That probability is 0.0294. Now, this was a two-tailed test. So because this was a two-tailed test, we're looking for the probability of a result at least this extreme on either side. So the probability of a result at least that extreme on this side plus the probability of the result at least that extreme on this side. So we found out that this probability is 0.0294. Because the normal distribution is symmetric, this is also 0.0294. And so that means that our p-value is not just 0.0294, but it's 2 times 0.0294. It's those two tails added together, and that gives us 0.0588. So 0.0588 is our p-value. All right, so what should the researchers conclude? Should they reject the null hypothesis? What does this mean in context? So again, we're going to compare the p-value with the level of significance. So the level of significance was, in this case, 0.05 was our level of significance. Again, that's alpha is our level of significance. Our p-value was 0.0588. And so we see in this case that the p-value was greater than alpha, the level of significance. So the probability of a result, at least this extreme in either direction, is greater than the level of significance, and therefore we do not reject the null hypothesis. We do not reject H0 because the probability of a result of observing this result, at least this extreme, was about 6%, was greater than our cutoff point, was not so unlikely given the hypothesis that the proportion of adults who believe texting while driving should be illegal is greater than 88%. So it could still be that it is still 88%. So we do not reject the hypothesis, the null hypothesis. What does this mean in context? We don't have enough evidence to say that the proportion of adults who think texting while driving should be illegal. Who think texting while driving should be illegal has changed. So we're not necessarily saying that it has not changed. We're just saying we don't have enough evidence to say that the null hypothesis is false. We don't have enough evidence to say that the proportion of adults who think texting while driving should be illegal has changed between 2004 and 2019.